Hi, I'm Bill Kinney, and this is the fifth video in a series on foundations of arithmetic, algebra, and graphing with a focus on real-life interpretation and application. Ideally, you watch these videos in order, though benefit can still occur even if you come in this series at any one spot. This is video number 5 again, although it's part 2 of a second sub-series of these videos. The first 3 videos focusing on addition and subtraction and their meaning and application. The next series of videos here focusing on multiplication of integers. Again, this is video number 5, part 2, about multiplication of integers. I want to go over quickly the problems that I discussed in the last video to highlight some other things about these problems. So this question says you are at a banquet and have 3 choices for the main course: chicken, beef, or vegetarian, 2 choices for the dessert, cake or pie. How many meals can you choose from? Many people intuitively see that the answer is 6, and that indeed is true, and there's 2 ways you can visualize it. With this thing called a tree diagram, or you might, I guess, just call this some sort of chart to see that the answer is 6, to see that you do 3 times 2. I want to highlight an algebra property here. Let's start with this chart here. I very easily could have drawn this chart in another way. I could have put the dessert up on top and the meal on the side. Oh, it's supposed to be an N there. And had, instead of 2 main rows and 3 main columns, I could have had 3 main rows and 2 main columns. My chart could have looked like this. And the boxes here would represent the 6 meal choices. Here you could maybe think of this chart as 3 times 2. Well, actually, a mathematician would probably be more likely to think of it as 2 times 3. 2 times 3, 2 rows, 3 columns. And here you could think of this one as representing 3 times 2, 3 rows and 2 columns. In both cases, you get 6. This is illustrating that 2 times 3 is equal to 3 times 2. They're both equal to 6. That's called the commutative property. Commutative property of multiplication. And I remember that name because I imagine the 2 and the 3 commuting back and forth to work. They can switch places. That's true. You can multiply in either order. It's pretty clear that can be done here in a picture like this. It may be less clear in the tree diagram. If you were going to see that you get the same thing with the tree diagram, you'd have to choose your 2 desserts first, either cake or pie, and then choose your 3 main courses, either a chicken, beef, or vegetarian. And there you'd think of this, I guess, as 2 times 3 equals 6 if you thought of it this way. It's a little less obvious that you're going to definitely get the same thing if you think about it with the tree diagram, but you do. Okay, so that's an algebra property that I want to highlight that we will find helpful later on when we get into more algebraic problems. With the bedroom problem, the area, your bedroom is 12 feet long by 10 feet wide. What's its area? Your bed is 6 feet long by 5 feet wide. The question is what area is left after you put your bed in the room. That means you first have to find the area of the bed. And we found that the area of the room was 120 square feet. And written like that, feet squared means square feet, because these are squares up here. There's a reason for that name. And the bed is 30 square feet. So overall, when you put the bed in the room, you've got 120 square feet minus 30 square feet is 90 square feet left over. I wanted to emphasize again, as I did in the last video, that when you do this subtraction here, you need to make sure that the units match up when you do an addition or subtraction. We also could think about the commutative property here, and it's pretty clear it's true. 12 times 10 is 120, and so is 10 times 12. And a reason, if you will, we could give is we could imagine drawing our room this way. So the long part is going up and down instead. Another interesting thing that I want to point out here is it's interesting that the bed has dimensions in terms of length and width that are exactly half those of the room, though I drew the bed so that those dimensions didn't quite match up here. If I was going to match them up, I'd put it this way. So this was 6 and this is 5, and I didn't draw that perfectly, but those linear dimensions, the one-dimensional things, are half the entire bedroom ones. 6 is half of 12, and 5 is half of 10. Thought of another way, 12 is 2 times 6, and 10 is 2 times 5. But when you look at the area of the whole room is 4 times more than the area of the bed. The area of the bed is 1/4 of the area of the room. Interesting. You might want to see if you can figure out why that happens, and if it would always happen if you've got some room of certain dimensions and you've got some bed or something else besides a bed that has half the length and half the width. Why would you always get the area of the bigger thing being 4 times the area of the smaller? See if you can figure out why that is. There's some algebra that could go on to help you figure that out. New problem here in this video. You earn $9 per week and work an 8-hour shift. How much money do you make during that shift? And if we assume that you work 5 shifts per week, how much money do you make in a week? 2 questions again. Answer the first question first. You earn $9 per hour and work 8-hour shift. Hopefully you intuitively see that you do a multiplication. 9 times 8 equals $72 is the answer. As far as writing it out, a standard way to do it is to write the 9 and the 8 with their units. And the standard way to write units of something like this, dollars per hour, is to put a dollar symbol and then put a horizontal line like this, and underneath put an hour symbol, HR. I'll explain that in a minute here. And then we have an 8-hour shift, so I can put 8 and then hours here, and I don't need to make that plural if I don't want to. And it doesn't matter, it's not a big deal if I make it plural. Don't worry about plural when you're dealing with units. And the final answer is 9 times 8 is $72, and it is traditional to put the dollar sign in front, but I think I'll put it here anyway. And I haven't explained fractions yet. Okay, that's a future video coming up soon. And I haven't explained dividing even. But you hopefully recall dividing. You can think of a fraction as being a division. And hopefully you remember that when you've got a fraction like this and something like this, that if you imagine these things as representing numbers, and they don't, the dollar sign, the hours don't represent numbers, they are units. 9 and 8, of course, are numbers, but if you pretend they're numbers, sometimes it's okay in math to pretend certain things just to help you do it, then you can actually cancel the hours and you see that the unit that you are left with is dollars, and that's where that comes from over there. If you wanted a visual as to why that's the answer, you could imagine making, well, a big picture where maybe each row in the picture represents the $9 you make in a given hour. 1, 2, 3, 4, 5, 6, 7, 8, 9. These are supposed to represent dollar bills. Maybe I should put ones on them. 1, 1, 1, 1, 1. And I do have 9 of them. And that's the first hour. 1 hour. Maybe I should call it first hour. The second hour, you again have $9 bills, etc. You'd have 8 rows for the 8 hours that you worked of $9 in each row. An array again, a chart if you will, showing you that 9 times 8 is the answer. Also 8 times 9 is the answer. It's commutative. Again, giving you $72 in the end.